Okay, hello class. Thank you for being on your best behavior with our sub today. You should be looking at your 7.2 size change notes. Here are the answers to your warm-up. If you're finding the lines of symmetry, remember to have arrows on both ends. Okay, we could count them. The directions didn't say to, but that's good practice for our quiz or for our test. This one has none since it's rectangular in shape there. And this one should look familiar from our quiz. There's our smiley face with only one line of symmetry. So what specific transformation will get us back to the original position of ABCD if we're doing this translation? Well, we have to think of the opposite. Since we slid it 4 to the left, we're going to slide it back 4 to the right. Since we slid it 7 down, we need to slide it 7 up. And we are now working with the prime first. And once we slide that shape, it'll go back to where ABCD started from. So what transformations are isometries? That would be reflections, rotations, and translations. Everything that was on our last quiz. But if they preserve orientation, that would just be a rotation and a translation. It would stay clockwise or counterclockwise, but with a reflection, it flips from clockwise to counterclockwise with each reflection. For a size change, that means to shrink or enlarge something. We are making things smaller or bigger. Certain properties here, we have the image and pre-image, and those will have the same shape, but not the same size. Right, in our last investigation, we ended up with 2 letter Fs. One was smaller, one was bigger. They changed size, but they still looked like the original letter. We call these shapes similar instead of congruent now. And we just use that squiggle from the top of the congruent sign. When we look at the angle measures, those do not change. You measured angle C and angle C prime in that investigation. They gave you the same degrees. Even though the sides changed length, your angles are always the same. Since your shapes are not congruent, size changes are not isometries. But they do still preserve orientation. If it was clockwise before the size change, it'll be clockwise after the size change. So now we can name 2 different shapes that will always be similar. That would be a square. Always keeping those angle measures the same, but we can change size, so those are just similar. And an equilateral triangle. So in the notation, we are going to use that capital S for size change, and we've got that subscript K value. So if our K value is greater than 1, then it enlarges the figure, it makes it bigger. If K is between 0 and 1, either a fraction or a decimal, then it shrinks the figure. We will not be using any negative K values. That was one of the questions from your investigation. You cannot do a size change with negative numbers because it's talking about the distance, the length of the sides. You can't change it to a negative distance. When this is applied to an ordered pair, we'd see something like our size change of K to the ordered pair X and Y. We will distribute that K value to both X and Y coordinates. So we end up taking, K times X and K times Y. We can also apply this to a drawing with a given reference point. So from the reference point, right, we can just abbreviate that RP. We need to measure And we will redraw / label the figure, multiplying each side length by k. To find new side lengths, and we do not change the angle measures at all. So we want to measure and draw a square 1/3 the size. So we're doing a size change of 1/3. We're going to use the lower left-hand vertex as the reference point. So I'm going to mark that as RP in my picture. So first, I'm going to go ahead and measure the length of all of my segments. If this is a square, okay, and I measure from, oh boy, the reference point here. Let's see, maybe it's easier on the computer. Okay, if I'm starting my measurements from the reference point, I can see that this segment is about 5.1 centimeters. I know that all of my sides are congruent since this is a square. So all of those sides are 5.1. I'm going to take that original length and multiply it by 1/3 or divide by 3. That leaves me with a side length of 1.7 centimeters. So I'm going back to my reference point, finding 1.7, putting a point there. I am also going to measure 1.7 from the reference point. Whoosh. This way. So here's my 1.7. Okay, if this is a square, that means over here from the line up would have to be 1.7. Okay, so now all 4 of these little sides will be congruent when I draw those lines in. So here's the sides of my smaller square now. How's that? So again, all of these side lengths are now 1.7 centimeters. Okay, take a look at those. We see that they are not the same size, but they're still that square shape. They are just similar. For the next one, we are actually enlarging this triangle. We did not do any of these on the investigation. We only shrunk the image. So we're going to measure and draw an equilateral triangle twice the size change of 2, and we're using this top vertex as the reference point. So if I measure this side right now and it's 3.1 centimeters, all of my sides would be 3.1 centimeters since it's an equilateral triangle. My new triangle needs to have side lengths of 6.2 centimeters. So I'm just going to keep it right there, mark at 6.2, and extend this triangle. Whoosh. Do the same thing, right? Since all of these sides were congruent, I can go back to that reference point. I need it to be another 3.2. We'd be going down to 6.2. Oh boy. Okay, so I can make another point there at the end of the ruler. Alright, so if I extend that out and connect, we've doubled those side lengths then. Oh, you know what? Yours may have been 3.6. Anyway, you can double check my measurements with your ruler on there. Just double whatever measurement you got in centimeters. So now if we just look at ordered pairs, we're doing a size change with 2.8. Remember, each vertex, each x and y coordinate gets multiplied by 2.8. So we're taking 2.8 times -5 for x, 2.8 times 12 for y, and we end up with -1433.6. Now we're working backwards. We're trying to figure out what k value got us times 22 and 43 gives us the 290.25. So if I think about it, I took k times 43, and that gave me a new y value, 290.25 if I'm solving this for k. I know that it's really 6.75. That means that I still have to take my k value times 22 to equal 148.5, and that's my new x coordinate. We also have a size change of 2/5. We're trying to figure out what x and y we originally started with. So if I took 2/5 x, that gave me my new x coordinate. Remember, to get rid of the fraction, we have to multiply by the reciprocal. Both sides get multiplied by 5/2. So here, multiply the top straight across. We get 3 times 5 to be 15. On the bottom, 4 times 2 is 8. We can leave that as a fraction answer. Then we have to take 2/5 times y. And that'll leave us with our y coordinate, -12/7. Again, multiply both sides by the reciprocal. -12 times 5 is -60 on the top. 7 times 2 gives us 14 on the bottom. We always got to make sure we reduce. Your y coordinate is -37. Okay, we can also use decimals. Hopefully we realize that that'll make our figure smaller. Taking my x coordinate times 7, or times 0.3, 0.3 times my y coordinate then, that gives us 2.1, -3. And we're trying to figure out what k value we have when we took k times 20 to get our new x coordinate. Divide both sides by 20. We end up with 5/2 or 2.5. That same 2.5 gets multiplied by your y value to give us -115. And lastly, we're trying to figure out what x value we have when we took 3/4 times x and it gave us -4/5. Multiply by the reciprocal. Good review of our algebra skills. -16 on top, 15 on the bottom. Same thing, we took 3/4 times that y coordinate, and that's how we got 2/9. Multiply both sides by the reciprocal. 2 times 4 is 8 on top, 9 times 3 is 27. So there's our original y coordinate.